Hello, 8th grade. In lesson 4.6, we'll be looking at the second of several theorems in this unit. This is called the conjugate root theorem. If you remember back in, I think it was 2 units ago, we discussed this idea of conjugates. So basically, if you have two complex numbers, a plus bi and a minus bi, those would be what are called conjugates of each other. Okay, it's just the exact same numbers on both the real and the imaginary part, except the signs on the imaginary part, this positive bi and negative bi, are opposites. Okay. Similarly, if you have irrational numbers, if you have a plus radical b, its conjugate would be a minus radical b. And we saw those were kind of special when we learned how to rationalize denominators. We learned that a conjugate times itself will give you only a real answer, or for rationals, if you take a conjugate times itself, you'd get actually just a rational number for the answer. And so stemming from that, we have what is called this conjugate root theorem. And all this theorem says is if a complex number or an irrational number is a root of a polynomial equation, then so is its conjugate. Okay, so what that means is if you have something like 5 plus 3i, and you know that it is a root of your polynomial equation, then by this theorem, 5 minus 3i must also be a root. Okay, that is what the conjugate root theorem says. If a complex or an irrational number is a root, so is its conjugate. So for 1 and 2 here, what I've done is I've just given you a few roots for these polynomial equations, and you're going to tell me based on those any others that you might know. So for number 1, I'm telling you that the square root of 2 is a root, as is the number 1 plus I. Okay, so the square root of 2, that is an irrational number, its conjugate would be negative the square root of 2. So by the conjugate root theorem, we know that negative radical 2 is also a root. We also have 1 plus I. It's a complex number. Because 1 plus I is a complex number, its conjugate, 1 minus I, must also be a root of this polynomial equation. So these are 2 additional roots based on that conjugate root theorem. Number 2, 3 minus 2i, I'm telling you, is a root. Therefore, its conjugate, 3 plus 2i, must also be a root. And 2 minus radical 5 is a root. Therefore, its conjugate, 2 plus radical 5, must also be a root. Okay, so that's what the conjugate root theorem says. Again, if I give you an irrational or an imaginary root, its conjugate must also be a root. We're going to use that theorem now and do something we did in the last unit, where I give you zeros or roots of an equation, and you're going to write the equation in standard form. This time, however, you're going to have to apply this conjugate root theorem because there may be some missing roots that you're going to have to fill in. So let's look at how this works for number 3. Number 3, I'm telling you that negative 4 and 2i are both roots of some equation. Okay? First thing you're going to do is you're going to look for any irrational or imaginary roots. Okay, I've given you the imaginary root 2i. So based on the conjugate root theorem, you know that negative 2i must also be a root. Now this is where you want to be careful, because I did give you negative 4 as a root. However, negative 4 is a rational number. Okay, there is no conjugate for negative 4. Okay, rational numbers do not have conjugates, so you can't say that positive 4 is a root. Okay, that doesn't work for regular rational numbers. Only for imaginaries and irrationals can you do that. So the only additional root here we have is negative 2i. And so now what we're going to do is we're going to take the negative 4, the 2i, and the negative 2i, and we're going to put them each as factors and write an equation in factored form. Okay, so I'm going to say p of x, or you could say f of x, equals, if negative 4 is a root, we know x plus 4 is a factor. 2i is a root, so we know x minus 2i is a factor. And also negative 2i is a root, so we know x plus 2i is a factor. Okay, so now I'm going to go through and multiply those. I'm going to go ahead and skip the x plus 4 part for a second, because I know if I multiply 2 conjugates together, it's going to make my life pretty easy. X times x is x squared. Negative 2i times positive 2i is negative 4i squared. You've got a difference of squares here. Okay, so the positive 2i and the negative 2i would cancel each other out on the outsides. That's why I didn't do those. And then x squared minus 4i squared is really the same thing as x squared plus 4. Remember, because I squared is negative 1. So now I'm going to take x plus 4 times x squared plus 4. When I do that, I get x cubed plus 4x plus 4x squared plus 16. And so my polynomial equation for this one would be in standard form. P of x equals x cubed plus 4x squared plus 4x plus 16. Okay, moving on. Similar process for number 4 here. We have 7 and radical 5 are the two roots I've given you. Based on the conjugate root theorem, you know that the conjugate of radical 5 would also be a root, so that means negative radical 5 is a third root there. So now I'm going to write the equation in factored form. P of x equals x minus 7, x minus radical 5, and x plus radical 5. Okay, just like the last problem, I'm going to multiply the conjugates together first. Okay, so this is going to give me x squared. Radical 5 times radical 5 is just 5, so that will give me x squared minus 5. And now I'll multiply these two binomials together. So this will be x cubed minus 7x squared minus 5x plus 35 when I put it in standard form. Okay, moving on to a bit more challenging problems here. Okay, so for number 5, we have 3 roots I've given you. I've given you positive 8, positive 2, and the irrational number 2 minus radical 3. So based on conjugate root theorem, you know that the conjugate of 2 minus radical 3 must also be a root. So that would be 2 plus radical 3. So this time we have 4 different roots that we're going to use the factor theorem on. Okay, so my factored equation is going to look like this. You're going to want to write kind of small because this is going to take a lot of room here. Just a fair warning. We know x minus 8 must be a factor. We know x minus 2 must be a factor. Okay, we also know that 2 minus radical 3 is a factor, so that means that x minus 2 radical 3 must also be a factor. So pay close attention to how I'm going to write this. Okay, this was my 0 originally, 2 minus radical 3. X minus the quantity, 2 minus radical 3, therefore must be the factor. So I'm putting that 2 minus radical 3 right here, putting that in its own little set of parentheses, and again, that's by the factor theorem. The other root, this was based on my conjugate root theorem, was 2 plus radical 3. So x minus the quantity 2 plus radical 3 must also be a factor. Okay, so to simplify this a little bit, I'm going to go ahead and multiply, first of all, my two normal binomials here. X minus 8 times x minus 2, you'll get x squared minus 10x plus 16 when you multiply those together. Here, if I distribute my negative sign, I get x minus 2 plus radical 3. Over here, I get x minus 2 minus radical 3. Okay, so now my task is going to be to multiply these two trinomials together here at the end. So this is going to take a little bit of work. So I've got my x squared minus 10x plus 16 that I'm just bringing down. Over here now, I'm going to take x times x, which is x squared, x times negative 2, which is negative 2x, x times negative radical 3, which is minus x radical 3. Okay, now I'm going to distribute this negative 2, so I get another negative 2x, I get a plus 4, and a plus 2 radical 3. And then finally with this radical 3, I get plus x radical 3, minus 2 radical 3, and then I have a positive radical 3 times a negative radical 3. That would just give me minus plain old 3. Okay, so a little bit of lengthy multiplication there. The nice part is a lot of these terms cancel here, so we're going to go ahead and look at those. I'm going to go ahead and bring down again this x squared minus 10x plus 16. And then in this mess over here, you can see that you have a negative x radical 3 here and a positive x radical 3 here. So these guys are just going to cancel each other out here and here. You also have the same thing happen with plus 2 radical 3 and minus 2 radical 3. Okay, so it really isn't as bad as it seems. The radical parts just completely go away. So you end up with x squared. We have a minus 2x here and a minus 2x here, so that gives you minus 4x. And then this plus 4 and minus 3 give you a positive 1. Okay, now here comes the really fun part. We get to do another trinomial times another trinomial. So now we're going to do this trinomial multiplication here. So x squared times x squared, which gives you x to the 4th. This would be minus 4x cubed. And then over here, plus x squared. Then distribute your negative 10x. We'll get negative 10x cubed plus 40x squared minus 10x. And then finally, plus 16x squared minus 64x. Remember how I said write small? And finally, plus 16. Okay, so one more time now, we're going to combine like terms here. And we'll get our final answer. P of x equals x to the 4th is just by itself. We have a minus 4x cubed and a minus 10x cubed, so that'd be minus 14x cubed. We have a plus 1x squared and a plus 40x squared is 41x squared. Plus our 16x squared gives us plus 57x squared. Negative 10x minus 64x is minus 74x. And finally at the end we just have our plus 16. So a lot of multiplication there, even more than we had in the last unit, but nothing that you can't do. It's just going to take a little bit of work to get down to that answer there. Okay, and of course, for a little bit more practice, I have number 6 here for you. Negative 2, 9, and then 4 plus 3i are the roots I've given you. This one's going to be very similar to number 5, except instead of an irrational root, I've given you an imaginary root. So if you know 4 plus 3i is a root, its conjugate 4 minus 3i must also be a root. And so we're going to start out by writing this in factored form. P of x equals negative 2 is a root, so x plus 2 must be a factor. X minus 9 must be another factor. 4 plus 3i is a root, so x minus the quantity of 4 plus 3i must be a factor. And then finally 4 minus 3i is also a root, so x minus the quantity of 4 minus 3i must also be a factor. Okay, when I multiply my two binomials here, I get x squared minus 7x minus 18. Here, I get x minus 4 minus 3i and x minus 4 plus 3i. And so now when I multiply these together, these trinomials, I'm going to get x squared minus 4x plus 3ix. Then I get another minus 4x, a plus 16, and a minus 12i. And then finally I get a minus 3ix, a minus 12i, and a minus 9i squared. Okay, just like the last problem, you're going to see some terms cancel over here. So let me go ahead and bring down this trinomial here, x squared minus 7x minus 18. And then over here, you're Your plus 3ix and your minus 3ix will cancel, as will your minus 12i and, whoops, it looks like I made a side mistake. This should be a plus 12i right here. Okay, we had a negative 3i times a negative 4. Yeah, that should have been a plus 12i. So, though, yeah, your I should always cancel whenever you're doing this kind of multiplication up here, just like your radicals did in number 5. So those go away. So now I have x squared. I have a minus 4x and another minus 4x is minus 8x. I have a plus 16 and then minus 9i squared, remember, is the same thing as plus 9. So 16 plus 9 gives me plus 25. Okay, what I'd like you to do now is finish this one up on your own. So go ahead and pause the video, do this last set of trinomial multiplication here, and then click play to check your answer, please. Do not skip forward and look ahead of the answer will. Okay, so if you did this correctly, you should have gotten the 9-term polynomial that I got here in black. And then your final answer should be x to the 4th minus 15x cubed plus 63x squared minus 31x minus 450. Okay, any questions you might have over this video, please shoot me an email with those, or at least jot those down so you can ask them next time I see you in class. And until then, have a nice day. You are all wonderful people. Take care.